The purpose of this video is to help you better understand the function of a clarifier and start you on your path towards effective clarifier operation. The purpose of a wastewater treatment clarifier is to slow the water down enough such that suspended particles can be separated out by the force of gravity. Mixed liquor, typically from aeration tanks, enters through a centrally located feed pipe. From there, the flow has two ways out. First, settled sludge leaves through another centrally located pipe at the bottom of the clarifier and is recycled back into the system or wasted. This is the underflow. The second way is over the overflow weir. In a properly functioning clarifier, overflow water should look very clear. Finally, grease, oil, and other floating material is removed by a skimmer on the surface. Without going into too much detail, some other important components of a circular clarifier include the rake arms, an energy dissipating inlet, the drive mechanism, a feed well, and a density current baffle. To review, particles, represented by our bug here, enter the clarifier suspended in the water. As they enter the clarifier, energy is effectively dissipated, allowing the bug, which is more dense than water, to slowly sink, while the water eventually makes its way to the top of the tank and over the weir. Pretty simple, right? Well, a lot of work goes into making sure that a clarifier functions correctly. And one powerful tool which can help with successful and effective clarifier operation is the state point or state point analysis. Let's go through what the state point diagram is and what it represents. The state point diagram consists of a horizontal axis, which represents the solid's concentration, X, measured in grams per liter. The vertical axis represents the solid's flux, G, measured in kilograms per meter squared hour. In this case, the solid's flux is the mass of solids passing through the clarifier in 1 hour, normalized to 1 square meter of clarifier area. Now that was a mouthful. Let's try and simplify it. Imagine a tiny clarifier with a surface area of only 1 square meter. The flux in this case would be equal to the total mass of solids passing through the clarifier in 1 hour. So if 1 kilogram of mass were to pass through in 1 hour, the flux would be 1 kilogram per meter squared hour. Now if the surface area of the tiny clarifier was doubled, but the same mass of solids passed through in the same amount of time, the solid's flux would be half. Why? Because it is normalized to 1 square meter of clarifier area. The amount of solids going through the clarifier didn't change, but the amount going through 1 square meter did, by half. By using flux, one can compare clarifiers of different sizes and loads on an equal basis. Now that we've covered both axes of the diagram, let's get to the 3 main components. The first component is the settling curve. This curve is developed by performing velocity settling tests at various concentrations of mixed liquor on site. However, empirical equations based on the sludge volume index, SVI, have been developed and are plenty accurate for using in deriving this curve. A smaller SVI, which represents faster settling, results in a larger settling curve. A higher SVI, which represents slower settling, results in a smaller settling curve. So what does it matter if the curve is larger or smaller? Well, we'll find that out in a minute. But now that we know that SVI is important in determining the settling curve, how do we determine the SVI, and what causes it to change? Well, the SVI can be determined by performing a settleometer test. Also, if you can, use a diluted sample to determine your SVI. This will allow for more accurate results, especially when the SVI is higher. SVI can be affected by a number of things. Almost all activated sludge develops some filamentous bacteria. However, sometimes the quantity of filamentous bacteria becomes abundant such that it settles poorly due to bridging of the flock. As a solution to this, some treatment plants have installed systems which allow them to dose chlorine into the recycle flow, which can significantly reduce the filamentous bacteria. Other process hiccups and influent contamination can also affect the SVI. The second component of the state point diagram is the overflow line. This line represents the flow through the clarifier. As the mixed liquor concentration increases, the flux increases also. The slope of this line represents the surface overflow rate, or SOR, which can be determined by dividing the influent flow by the clarifier surface area. It is important to remember that this line can be adjusted by changing the influent flow rate. A higher influent flow rate results in a steeper slope up. A lower influent flow rate results in a flatter slope. The third and final component of the state point diagram is the underflow line. The y-intercept of this line represents the solid's loading rate, or SLR. The x-intercept of this line represents the expected underflow concentration. The slope represents the solid's underflow rate, or SUR, which is calculated by dividing the RAS flow by the clarifier surface area. This line can be adjusted in two ways. First, by changing the RAS rate, you can affect the slope. A higher RAS rate will result in a steeper slope down. A lower RAS rate will result in a flatter slope. Also, the location of this line can be adjusted by changing the solid's concentration entering the clarifier. A higher concentration moves the line away from the origin, with the opposite occurring with a lower concentration. Putting all the pieces together, we have our full state point diagram. So, how do we use it? We start by defining the actual state point. This is the point where the overflow rate line and the underflow rate line intersect. To ensure proper clarification, we want to make sure that this line falls underneath the settling curve. If this point falls above the settling curve, the clarifier is failing in clarification. In other words, the solids entering the clarifier don't have enough time to settle before going over the effluent weir. This could be caused by increased flows, not enough RAS flow, a high SVI, or a combination of any of them. It is not a good place to be. At this point, the clarifier is not doing its job at all. However, getting the state point under the curve isn't the only goal. In order to ensure proper thickening of the sludge, we want to make sure that the entire underflow rate line to the right of the state point falls under the settling curve as well. If the state point is under the curve but the entire underflow rate line isn't, the clarifier is failing in thickening. This means that sludge is settling in the clarifier but isn't being removed fast enough. Under these conditions, the sludge blanket would rise in the clarifier until solids are passing over the weir. Thickening failure, like clarification failure, can be caused by high flows, low RAS, high SVI, or any combination. So if either of these scenarios should occur, and you were to fail in thickening or clarification, there is some good news. The system will eventually fix itself. How? Well, if solids are passing over the weir, the concentration of the system will decrease. And as we've already covered, a lower mixed liquor concentration will move the underflow line back towards the origin and eventually under the settling curve. The bad news is, if this happens, you probably just violated your permit. So the goal is to avoid either types of failure. Let's take a look at some real-world scenarios now, where the state point diagram can help you determine what actions you can take as an operator. For this exercise, we are going to use an actual state point model. Let me bring it up. This is one version of an interactive state point diagram that can be used as a tool in clarifier operation. As you can see, this model has three methods for developing settling curves. The first is based on actual measured clarifier characteristics. The second is an approximation developed by Dr. Glenn Daiger. The third is a modification on the Daiger model called the Daiger-Roper. Let's simplify things and clear some values out of the other models and use just the Daiger model only. The Daiger model allows you to construct an approximate settling curve based on the SVI. We're going to assume that we have some decent settling sludge here, coming in with an SVI of 250. Let's make the clarifier diameter 80 feet and specify that only one is in service. For this scenario, let's have everything going smoothly with an influent flow of 3 mgd, a RAS of 50% of the influent flow, and a mixed liquor concentration of 2,500 milligrams per liter or 2.5 grams per liter. Let's clear the second state point values now so we can focus on our single state point. And as you've probably noticed, this model adjusts the graph automatically and immediately, allowing us to quickly evaluate how things are going. Well, we see that in this case things are going quite well. Both the state point and the underflow line fall under the settling curve. Man, life is good. The sun is shining, birds are chirping, and the air smells fresh. Well, as fresh as a wastewater plant has to offer. But just like any rainstorm can ruin a perfect day, it can also ruin your smoothly operating clarifier. So it's a rainstorm. Hits your system and the flows begin to rise. Before you know it, your influent flow has risen to 4 mgd and your RAS pumps don't automatically adjust with the flow. For this, we need to override the RAS rate. We see that 50% of 3 mgd is 1.5 mgd of RAS. Now we need to enter in the value in gallons per minute in the override box down here, which conveniently gives us the conversions to mgd. And because we're really smart, we know that 1.5 mgd is 1045 gallons per minute. So we can enter that in here and it overrides up here above. And now we can change our flow to 4 mgd. And as you can see, our state point stays under the curve, but our underflow line doesn't. We know we are going to fail in thickening. So what can we do? Well, let's see. Say we actually have a little bit more capacity in our RAS pumps and can turn those up to 2 mgd. Well, does it help? Yep. As we discussed, increasing the RAS flow results in a steeper underflow rate line, and we're back in good shape. Good job, crisis averted. But what would happen if flows continued to rise? Let's say to 5 mgd. Well, in that case, we'd be failing in clarification as well as in thickening. Also, as mentioned, we've already maxed out our RAS pumps, so we can't pump any more out of the clarifier. In this scenario, there are two options. First, if the flow increase can be predicted well in advance, there exists the option to preemptively waste solids to reduce the mixed liquor concentration. In this case, if the mixed liquor concentration was preemptively reduced to 2.2 grams per liter, we see that we'd be back in the safe shelter of the settling curve. However, this is not a realistic approach to dealing with unexpected high flow events that occur from time to time. Typically, the only other option available in this scenario is dosing your RAS line with some chlorine. A quick dose of chlorine in the RAS can attack the filamentous bacteria and lower the SVI. If the chlorine dose was able to drop the SVI down to 200, we'd find ourselves back in the safe zone. However, this option is only available to treatment facilities with the proper equipment installed. So now we've seen some ways to avoid failure. But the state point diagram can also help optimize clarifier operation, not just prevent problems. Let's go back to our nice, properly functioning clarifier. The SVI is back to 250, the flow is 3 mgd with a RAS running at 50% or 1.5 mgd, and this time let's say that we've wasted some and our mixed liquor concentration has dropped to 2,000 milligrams per liter or 2 grams per liter. We are way under the curve both in the state point and the underflow rate line. Life is good, right? Birds are chirping and so forth. Well, yes, they are, but it could be better. You see, the gap between the settling curve and the underflow rate line represents wasted energy. What this means is we are recycling more than we need to. As we mentioned earlier, a lower RAS flow results in a flatter underflow rate line, so let's change that. In this case, we can drop our RAS to about 30% or 0.9 mgd. And still be under the line. Does this mean we should always drop the RAS down such that we are as close to the settling curve as possible? Actually, no. It's always good to have a safe bit of buffer there. Also, if the sludge is kept in the clarifier as long as possible without failing, there's a chance that denitrification may occur, which could cause your sludge to float due to the generation of nitrogen bubbles. But a very large buffer is unnecessary and represents wasted energy. Well, that was a great start in using the state point analysis to better operate a clarifier. Now take some time to run through some of your own scenarios. I'm sure you'll find this method beneficial, and you might even learn something new by using it.